Hi guys, so my name is Mohit and I've decided to start a YouTube channel. It's primarily about mathematics and physics, and I'll focus on showing you proofs about different theorems or basically about different theorems and stuff that you've learned in high school or maybe in first or second year university. And most of the high school students that I personally know of or that I've personally taught will take these theorems for granted, but it's actually very important that we prove these theorems before we use them so frequently in mathematics. And similarly in physics, I will show you a few different proofs, but most of the content that I'll upload about physics will focus on showing you the solutions to some hard problems that I've encountered so far in my undergraduate degree. So the question that I've picked today is a question that is actually quite simple, or the content of the question is actually quite simple. We use it pretty much every single day whenever we are doing calculus or anything related to calculus. So this is the theorem over here. It says let f of x be equal to x to the power of n, where where n is any positive natural number. And we want to show that the first derivative is equal to n times x to the power of n minus 1. And the second question is literally the same question, but instead this time, instead of n being a positive natural number, n is a real number. And the idea is basically to prove that the derivative is indeed n times x to the power of n minus 1. So before I show you the solution to this problem, I would encourage you to pause the video at this time and try to solve these questions on your own first. So I hope by now you've paused the video and you've attempted these questions on your own. And if you got the solution, congratulations. And we'll see if I do the question in the same way as you did, because there are multiple ways to solve any one of these questions. So let's begin with the first one. Um, so there are a couple of ways to solve this first question. I'm actually only going to show you one of those ways, which I think is the simpler of the two methods. So once again, our function over here is x to the power of n, and n here is any positive natural number. And what we want to show over here is that the first derivative is equal to n times x to the power of n minus 1. Now, one of the methods that you could do this, which is absolutely correct, is to actually use the definition of the derivative over here, which is to say that the first derivative is equal to limit as h approaches 0 of f of x plus h minus f of x divided by h. And then you could evaluate this limit on the right hand side and you will get the correct answer. But I don't want to do that, especially because it uses the binomial expansion on the right hand side. There is actually an alternate method which I believe is simpler than this one, so I'm going to focus on using that one. And that method essentially relies on a proof by induction, which is what I'm going to show in this video. So I'm going to present a proof by induction. My base case over here is going to be n equals 1. So when n equals 1, my function f of x is just equal to x to the power of 1, which is just x. And the derivative of x is just 1. Now notice over here that the argument is not circular. In computing this derivative, I'm actually not using this identity. You could think about it this way, that in order to compute this derivative, you actually graph the function x, y equals x, which is just a straight line. And then you use the traditional formula for rise over run, traditional formula for a slope, which is rise over run. And you got that the slope is 1, which means that the first derivative is also 1. So in other words, the argument is not circular. Then you can go ahead and do your induction step now. So my induction step over here is going to involve fixing n to be any natural number. So I'm going to fix n to be any positive natural number. And then I'm going to assume, oh, yeah, okay. So I'm going to assume that that if f of x is equal to x to the power of n, then the first derivative is equal to nx to the power of n minus 1. And I'll show that if f of x is equal to x to the power of n plus 1, then f prime of x is equal to n plus 1 times x to the power of n. And this will complete the proof. So let's begin. So let's assume that I have f of x, and let's say that f of x now is equal to x to the power of n plus 1. Ideally, I should have named this some other function like g of x, just to make sure that these two functions are different, but it's okay for now. Now notice that f of x equals x to the power of n plus 1 is the same thing as f of x is equal to x times x to the power of n. And now I'm going to compute the derivative using the product rule. So the derivative of x is just 1, and then I'm going to multiply that by x to the power of n, plus the derivative of x to the power of n by assumption is nx to the power of n minus 1, and then you multiply this by x. And now all I have to do is evaluate this. So this is going to become x to the power of n minus 1 times x is just x to the power of n using the laws of exponents. And then I can factor out nx to the power of n, and I'm left with n plus 1 times x to the power of n, which is precisely what I wanted to show. And this completes the proof. So now one of the very important questions over here that some of you might wonder is, why does this proof work? Like, why can I assume over here that the derivative is n times x to the power of n minus 1? And this is fundamentally a question about why induction works in general. I'm not going to show you a rigorous proof in this video. I might upload it in the upcoming videos about why induction works. But you can think about it this way, that clearly the identity hold for n equals 1. You could think about this. I could actually complete the proof over here. 1 is the same thing as 1 times n to the power of, x to the power of 1 minus 1, which is the same thing as n times x to the power of n minus 1. N in this case is, of course, just 1. So the idea is that clearly this proof, or this identity over here, works for n equals 1. Now what this step over here says that if it works for the integer n, then it also works for the integer n plus 1. So in this case, I've shown that it works for 1, thus it will work for 2. But if it works for 2, it must work for 3. If it works for 3, thus it must work for 4. And then you can keep on going on in this way. And the reason behind it is that n over here is completely arbitrary. It can be any positive natural number. So this is how you actually, this is one way to show that the derivative of x to the power of n is n times x to the power of n minus 1, given that n is any positive natural number. However, I actually personally like another method, and that's this other method is actually also used to prove part 2. So everything remains the same. My function is still x to the power of n. In this case, n is a real number. Oh, by the way, strictly speaking, n should be defined before I define f of x, both here as well and here. But I'm gonna look over that for now. Okay, so now what I want to show in this case is that the first derivative is equal to n times x to the power of n minus 1. Now what I'm going to do over here is I'm going to use a little bit of a trick over here. So observe that if f of x is equal to x to the power of n, then ln of f of x, so I'm just going to take the ln of both sides, must be equal to ln of x to the power of n. And of course this implies that ln of f of x is equal to n times ln x. This is just one of the laws of logarithms. I can bring this power down in the front. And now I'm going to take the derivative of both sides. So on the left hand side, I have to apply the chain rule. The derivative of ln of f of x by the chain rule is just f prime x divided by f of x. And the derivative of the right hand side, n is just a constant, so it's just going to come down as it is. And then ln of x is 1 over x. The derivative of ln of x is 1 over x. So what I get over here is that f prime of x is equal to n times x to the power of negative 1 times x to the power of n. The reason why I have an x to the power of n over here is because I multiplied this f of x on the right hand side, and then f of x by definition is just x to the power of n. So I can replace that with x to the power of n. And now if you just simplify this, you're going to get that the first derivative is equal to n times x to the power of n minus 1. And notice this does complete the proof. We'll also notice that in order to prove number 1, in order to prove this first theorem, you could have actually just used the proof that I showed you right now. And the reason why that is the case is because the second theorem, or this the second proof, actually applies to all real numbers. So this applies to all real numbers, whereas this one only applies to all positive natural numbers. And since the set of all positive natural numbers is a subset of the set of all real numbers, anything that is true for all real numbers must also be true for all natural numbers. So it is, you could have just done proof 1 and proof 2 the same way and just use this method to show that the derivative of x to the power of n is n times x to the power of n minus 1. So, I mean, just to show you how to use this theorem in practice, which I'm pretty sure most of you have been using for quite some time, it's, for example, let's say I have x to the power of pi. Now the idea is the same by the theorem that I've proven above, f prime of x. In this case, of course, my n is equal to pi. Right? So all I have to do is bring the pi down times x to the power of pi minus 1. And this is the first derivative. So once again, this is quite a simple proof, nothing complicated over here. You let me know how if you were able to solve these questions, and if you have some other method in mind to solve either one of these questions. Like, I personally don't know of any other method to actually show that the property is true for all real numbers other than the solution that I've already shown. I know that there are other methods to prove the identity over all the natural numbers. Yep, so I hope you enjoyed the video, and I'll see you in the next video.